This is Ishan Dalal, second year master's student in the Electrical and Computer Engineering department at the University of Florida. I'm giving this presentation for the report of a project in wireless communication, and the topic of my project is a broad study of a space-time division coding scheme, the Alamouti code. So I will begin with discussing the problem under study. In this case, it is the multipath propagation. It is a very common phenomenon in wireless communications wherein multiple signals they cause the receiver to receive not just one clear signal but superposition of many signals, and thus it renders the system unreliable for communication. Uh, so in the next sections I will be discussing about the various approaches that have been developed over the years to counter this multipath propagation, like the time diversity scheme, the frequency diversity scheme, and so on. Then I will come to a section wherein I will introduce my proposed approach, which is the Alamouti coding scheme that is based on the space-time division coding scheme. And it will be followed by a section on a mathematical background or a foundation of how the Alamouti code works. The Alamouti code was first developed by engineer named Alamouti in the year of 1998. In the next section, I will be discussing about the work that has been done in the past, wherein the Alamouti code has been utilized to obtain an accurate average bit error rate for binary phase shift keying modulation using a moment generation function. And in some other cases, this space-time coding scheme has been used to analyze the performance of multiple in, multiple out antenna subset selection. Next, I will be showing my MATLAB code that I have developed for the Alamouti coding scheme. I have developed it for two implementations. One is two transmitter, two receiver implementation, and second is two transmitter, one receiver implementation. And simulation will again be shown in MATLAB, wherein the output of the simulation would be a graph showing the relationship between the bit error rate and signal to noise ratio for these two implementations that I said earlier. Once I get all the results from the simulation, I will compare it with the results of BER versus SNR of a traditional scheme wherein one transmitter and one receiver is used, and the maximum ratio combining scheme, which is another diversity scheme that is being used on a very large scale, which employs one transmitter and two receivers. And after this analysis and comparison, I will give light to key observations, and then there will be a conclusion section which will summarize the findings of this report, and lastly it will be followed by the acknowledgements in the references section. Moving on, let's discuss about the problem under study. Now, wireless communication has been a fast developing area in the recent years. It has made a huge impact on the lifestyle of people, starting from working of satellite operations, mobile phones, wireless data, radar system, wireless communications. There has been a tremendous growth in this field. But along with the growth, there have been many challenges that needs to be overcome in order to have a reliable, error-free transmission from transmitter to the receiver. And of the many problems that wireless communication domain faces, channel fading and interference are the most important ones, and the multipath propagation that I talked about earlier has much to do with these problems. It's a very common phenomenon in wireless communications. Now, talking about the multipath channel fading, it is caused due to the deviation of the attenuation of a signal when it travels through a propagation media. It is modeled as a random process since it varies with time or frequency of a radio wave or even geographical location. Multipath fading is one such type of fading that occurs due to multipath propagation. Communication channel that experiences this kind of fading is called a fading channel. Now, in case of multipath interference, the radio waves that travel from transmitter to receiver through multiple paths many situations, and this leads to interference which can either be constructive or destructive depending on the individual phases. And when this signals or when this multipath signals they travel through these different paths and result into constructive or destructive, they can either be resolvable, that causes inter-symbol interference, or unresolvable, that causes channel fading. Disruptive multipath propagation will definitely cause channel fading. Now, going into details about channel fading, uh, it has been seen that many times the radio signals, they do not traverse only one path to go from transmitter to the receiver antenna, but they follow numerous other paths. And this happens mainly due to the obstructions in the field that cause the reflection and refraction, atmospheric ducting, or atmospheric reflection. The receiver, however, is unable to distinguish between the original line of sight path and the other paths due to multipath propagation. Each of these paths have different amplitudes, delays, directions, and phase shifts. Now, there are two primary types of channel fading. First is the Rayleigh fading, and second is the Ishan fading. In case of the Rayleigh fading, the magnitude of the signal traveling through a communication channel will vary randomly, or in other words, fade according to the Rayleigh criteria. It is found to be most applicable when there is no dominant propagation along a line of sight between the receiver and the transmitter, and it is viewed as quite a reasonable model for ionospheric and tropospheric signal propagation. In case of Rayleigh fading, there is a partial cancellation of radio signals taking place by itself while the signal is traveling or traversing through the channel, and the signal arrives at the receiver by different several paths, and at least one of the paths is changing. It is The Rayleigh fading is found to occur when one of the paths, typically the line of sight path or the signal, is much stronger than the others. Now let's talk about the existing approaches that are out there in the industry that are used to solve this problem of multipath propagation. The multiple and multi-route systems, which has been a very important source of technology in wireless communications, has been employed on a very large scale because it not only improves the reliability in terms of error-free bit propagation, but also it improves the multiplexing gain through the diversity gain. And how it does is that it uses multiple antenna systems at the transmitter and the receiver ends, which improves the multiplexing gain, diversity gain, the array gain, and at the same time it results into a reduction in transmission errors and quite a big improvement in channel capacity. And because of these reasons, it has been used in new technologies in wireless communications, which include the 4G wireless standards like the WiMAX, or the long-term evolution, that is the LTE, that has been used on a large scale in many smartphones, tablets, laptops, etc. It is found that the system that is using this MIMO-enabled technology, its throughput is improved at no additional cost of bandwidth or transmitted power. The MIMO schemes can be broadly categorized into three parts. First is the pre-coding, second is the diversity coding, third is the spatial multiplexing. The focus of this project would be the diversity coding. Now, moving on with the diversity coding, so the diversity schemes, they employ the fact that the reliability can be increased by using different characteristics of the transmitted signal in different communication channels. Multiple copies of the same transmitted signal can be received at the receiver, and at times a forward error correction code may be introduced in each of these channels. In other words, the diversity scheme turn the problems caused by multipath propagation into solutions that aid in better transmission and reception of signals over the propagation media. The schemes also introduced a parameter diversity gain, which is basically an increase in the signal to interference ratio measured in decibels. And as I said earlier, there are various types of diversity schemes. There is the time diversity, frequency diversity scheme, then multi-user diversity scheme, polarization diversity scheme, cooperative diversity, and the space diversity. Now, in case of a time diversity, there are multiple versions of the same signal which are transmitted at different time instants. While in the frequency diversity, transmission of signals takes place over several frequency channels, or it is spread over a wide spectrum. Now, when signals are transmitted, are received by antennas of different polarization. It is called the polarization diversity. Opportunistic user scheduling at transmitter and receiver is the basis of multi-user diversity. And in case of cooperative diversity, there is a cooperation of distributed antennas at each node that contributes to the antenna diversity gain. In case of the space diversity, that is the last in this list, the transmitted signals propagate over different propagation paths, and it is also known as the antenna diversity. In this diversity technique, two or more antennas are required for improving the reliability over the transmission channel. Now, one of the very first schemes that was developed was the spectral diversity technique. It's a pretty well-known method for implementing multipath propagation in wireless communications, and one of the schemes that I would be using later to compare my results is the maximum ratio combining scheme, the MRC scheme. And this MRC scheme is based on the spectral diversity technique, and it's a type of a receive scheme. In MRC, the signals received from various receive antennas are weighed, added, added up to maximize the signal to noise ratio, and it uses one transmitter and two receivers. Now, coming to the focus of or the coming to the target scheme that this project focuses on, the space-time diversity. So the space diversity has a subclass called the space-time diversity, and in this diversity, the fact that the transmitted signal is not only corrupted by interferences or fading, but also due to thermal noise at the receiver is taken into account. So at the receiver also there will be some signal copies which are better than the others. So this space-time coding combines all copies in order to get maximum information from the transmitted signal. And there are two types of space-time coding scheme. One that uses the space-time trellis code, and second that uses the space-time block codes. Now the space-time trellis code distributes the trellis code over multiple antennas and provides both coding gain and diversity gain. Whereas in the space-time block codes, diversity schemes act on one block at a time. In this scheme, however, coding gain is not obtained, but only the diversity gain is obtained. And as compared to the single antenna system, a multiple antenna system provide better error rate improvements. It was found originally that the space-time codes were based on trellis, but later simpler block codes were employed by Alamouti, Tarok, Zafarkani, and Kelterbank. In case of the space-time block coding, it is found that the transmitted data is divided into blocks, and these data blocks are received by receiver antennas which are spaced across time. Now, talking about the space-time coding, it can be represented by a matrix where each row represents a time slot and each column represents the antenna's transmission over time. Now, this matrix you can see on the right hand side of the slide. In this matrix, the Sij corresponds to a modulated symbol where the antenna J transmits in time slot I. In all, there are total T time slots, NT transmit and NR receive antennas, and the length of this block code is T. The space-time coding takes into account both spectral and temporal diversity that adds up to significant gains. And this diversity scheme basically gives rise to a multiple in multiple out system where more than one transmit or receive antennas are used. The MIMO system is a part of a smart antenna technology. Now all this leads to our proposed solution of Alamouti code, because Alamouti code is based on the space-time block coding scheme. This Alamouti code was first introduced by Siavash Alamouti in the year of 1998. The Alamouti coding scheme is based on the MIMO system where two transmit antennas are used. For the designing of this scheme, no knowledge of channel is required, which makes it even more simple to design. The Alamouti code is the only block code that receives the maximum diversity gain at a data rate of 1. The implementation of Alamouti codes in wireless communication has brought about huge impacts in the field of wireless communication. Now, talking about the Alamouti code itself, it's a transmit diversity scheme where original data to be transmitted is spread among a number of transmitters. Let us consider a transmission sequence of S1, S2, S3 up to Sn. Now, in a regular transmission scheme, S1 is sent in first time slot, S2 is sent in second time slot, and so on. But in case of the Alamouti coding scheme, at a given symbol period, two antennas simultaneously transmit two symbols. So the antenna 1 will transmit S1, antenna 2 will transmit S2 in a given symbol period, and in the next symbol period, antenna 1 will transmit minus S2 star, and antenna 2 will transmit S1 star, where the star corresponds to the complex conjugate operation. Now it can be observed that even though the symbols are grouped into two, still two time slots are required to transmit two symbols. So this explains why the Alamouti code does not have a change in data rate while achieving maximum diversity gain. The Alamouti scheme is mostly modeled into two transmitters, one receiver scheme, and two transmitters, two receiver scheme. Now let's have a peek into the mathematical foundation of the Alamouti code. First, let's talk about the two transmitter, one receiver scheme. Now, as the name says, this Alamouti coding scheme has two transmitters and one receiver. Now, for this project, the channel has been taken to be a Rayleigh fading channel. For the modeling of Alamouti scheme, the channel between one transmit antenna and the receiver is independent of the channel between the other transmit antenna and the receiver. And each of these channels are there very randomly with time, but the channel is assumed to be constant over two time slots. The model for 2T1R Alamouti coding scheme is shown on the right hand side. Now, based on this model, the equations for the transmitted side of the signals are h1 of t is equal to h1 of t plus capital T, h2 of t is equal to h2 of t plus capital T, and the corresponding received signal equations are given by y1 that is equal to r of t that is equal to h1 s1 plus h2 s2 plus n1, and y2 is equal to r of small t plus capital T that is equal to minus h1 s1 into s1 star plus s2 into s2 star plus n2. Now here the n1 and n2, they correspond to noise in the first and second time slots. H1 corresponds to the channel between the first transmit antenna and receiving antenna, and S2 corresponds to channel between the second transmit antenna and the receiving antenna. Y1, Y2 are the received signals, and S1 and S2 are the transmitted symbols. Now all these equations can be represented in matrix form, and it is shown in the given slide. Now here H is defined as the H is defined in matrix format as shown, that is H1 H2 H2 star minus H1 star, and also we can obtain the pseudo inverse form of the H matrix, and the term H of H into H in matrix form is given as you can see. Now after simplification and uh, all the calculations, we obtain the decision statistics that are given by the maximum likelihood, and we find that the above equation denotes an estimate of transmitted symbol, and it's quite similar to the equation that is there for the maximum ratio combining scheme. And that is what I had said while I was discussing the spectral diversity technique, that the maximum ratio combining scheme is very similar to this technique. The matrix h of h into h is a diagonal in nature. Its advantages are that there is no crosstalk between symbols s1 and s2, and also the noise term is the white Gaussian noise. Moving on, mm, the next implementation is a two transmitter to receiver scheme, and as the name suggests again that it uses two transmitters and two receivers. The equations of this 2T2R scheme are very similar to the 2T1R scheme, and in the first time slot the received signal is given by this matrix, which is a product of the H and S, and which is added to the N matrix, that is the noise matrix. And the received signal in the second time slot is also given in the same manner. The Y1I term here represents the received signals in the first time slot, and the Y2I term represents received signals in the second time slot. N1I terms, they denote the noise for the received signals at the first time slot, and the N2I term denotes the noise for the second time slot. S1 and S2 are transmitted signals. Hij parameters denote channels between each pair of transmitter and receiver. And so all these equations can again be obtained by combining both received signals, and it can be combined into a matrix form that is shown in the given figure. And the corresponding pseudo inverse matrix of H can be obtained. The model for the 2T2R scheme is shown on the right hand side of the slide. And after simplification, we are able to get the transmitted symbol estimation. Now let's talk about the work that has been done in the past in this domain. In first of the works, in one particular, as you can see, it is written as one. Here we are talking about a paper wherein the Jamali and Conan they came up using receiver antenna selection with extensive performance analysis of 2x2 wireless MIMO Alamouti coding scheme. They found out an accurate average bit error rate for binary phase shift keying modulation using a moment generation function. In the second part of the research, they also derived the order statistics associated with the instantaneous signal to noise ratio at two selected antennas. The study concluded that the analytical bit error rate expression for the scheme were matching with simulation results, which can extend it to include effects of mutual coupling and spectral correlation between antennas. In another related work, I was able to find this paper wherein Gore and Polraj they employed this space-time coding scheme to analyze the performance of MIMO antenna substrate selection. The study focuses on antenna substrates being selected on basis of exact channel knowledge, assuming that orthogonal space-time block code transmission with importance given to the Alamouti code. The study concluded that the antenna substrate selection, being a low-cost, low-complexity technique, keeps the diversity benefits of multiple antennas while addressing the issue of optimal MIMO substrate selection in flat fading channels with space-time coding. Now moving on to the implementation and the simulation of the Alamouti code based on the mathematical foundation that I talked about earlier. Here a MATLAB version R2010A is being used to implement and simulate the programs for 2T 1R and 2T 2R. Now, this programs for the 2T 1R and 2T 2R schemes of Alamouti have been coded by myself in the MATLAB, and it has been simulated. And the output of the simulation would be a graph showing the relationship between the bit error rate and the signal to noise ratio in decibels. Let's have a look at the programs and then I will run the simulation. So these are my which will do the programs. This is the program that has been developed for the Alamouti scheme of 2 transmitter, 1 receiver channel. Here the iteration here the number of iterations have been kept as 10,000, and the number of bits per symbol are 1. And again it has been done using the Alamouti code, as I said. Then the errors are also computed, and also the bit from the errors we can get the bit error rate. Similarly, for the 2T 2R scheme, it is quite similar to the first case. The only difference, I think, is the number of transmitter and receiving channels. Apart from that, the entire code is the same. And one more program that I created was the generation of metrics. This function basically builds metrics of relay channel coefficients. And finally, I created a script to run all these programs at once. This script runs both the 2T 1R scheme and 2T 2R scheme and plots a graph of BER versus SNR. So now let's run it and see what happens. Now this simulation will take some time, so I will stop the recording and restart it once it's done. So this is the graph of BER versus the SNR for 2T 2R and 2T 1R. Now in this graph, the green lines they indicate the performance of the 2T 1R channel, and the light blue line indicates the performance of 2T 2R channel. And it is found that the BER performance of 2T 2R, as you can see, is much better than the 2T 1R performance. So that is what it has been presented over here. Now comparing this with the MRC scheme of 1T 2R, and the MRC scheme is shown in the green line. It is seen that the MRC scheme is MRC 1T 2R scheme is better, like the BER performance is better as compared to the Alamouti 2T 1R, but the Alamouti 2T 2R is again much better than both the other schemes. And lastly, comparing it with the traditional scheme, which is the 1 transmitter 1 receiver, the 1 transmitter 1 receiver is the worst performer among all the 4 different schemes, and Alamouti 2T 2R scheme is the best performer in terms of the bit error rate. Now coming to the tabulated format, these are the results that I am getting. As you can see that the 2T 2R is much better as compared to the 1T 2R and the other schemes at different signal to noise ratio values. So the key observations that I can take out from this particular study are that compared to the maximum ratio combining scheme of 1T 2R, The Alamouti space-time block coding of 2T1R has 3 decibels poor performance, while the BR ratio of Alamouti 2T2R is much better than the maximum ratio combining scheme, since it results in a diversity order of 4. M receiver antennas has a diversity order of 2M. Because of that, the result of diversity order is 4 in case of 2T2R. Compared to the traditional mode of transmission 1T1R, both the MRC and the Alamouti schemes have better BR performance because of the increase of diversity gain as well as reliability due to the use of more than one transmitting and receiving antennas. Now, concluding the report, we can say that compared to the maximum ratio combining scheme and the traditional transmitting systems, the Alamouti coding scheme has a much better BR performance. And also, it is the only orthogonal space-time block coding scheme that achieves a maximum diversity gain with a data rate of 1. And due to this property of Alamouti scheme, it is advantageous over higher order STBCs, even though they have better BR performance. However, it has been found that the Alamouti schemes performs best with 2 transmitters, and its performance will decrease or it decreases when it is used with more than 2 transmitters. Acknowledgements. I would like to thank Dr. Dapengu for teaching us various important concepts of wireless communication, multipath propagation, and also helping us in exploring the project topics to develop the practical know-how of how things work in the industry. Definitely, this project has helped me gain knowledge and experience which I can apply in the industry. So thank you again, once again. These are the references which I had mentioned in the related work. Detailed references are given in the project report, wherein the links of the Alamouti paper could be found out. Thank you.